here to chapter 5, continuous random variables. Um, so as it says, it's continuous. We're moving on from discrete, where values have to land on 1, on 2, on 3, on 4, but instead they can be an infinite number of numbers. So think more of length, height, width, time. So that's what we're going to focus on more this time. Now, notice that we're going to refer to um, these distributions as functions, right? They're no longer discrete in value. So, where we formerly had a distribution that would be this, and so on and so forth, and this would be a bin, right? A bin of values, or it would either be 0 to 1, or it would be just 1. Now, we're going to have a single value. We're going to have 1, but we're also going to have 1.1, and there's also going to be a number in between there, right? 1.05. And that's going to continue on, and every single point on here is going to have a probability. What's that going to lead to? It's going to lead to error. It's going to lead to a function, right? So it is continuous. There are no gaps anywhere in there. So absolutely every outcome has a probability. And here is the CDF. I've also made a few hints to this, but remember, instead of the key here is cumulative, right? We're going to be adding these probabilities together. So this, when you take each slice, and instead of moving it, instead of giving it its own probability, you're going to say, this is now the probability that we have this or anything less. This or anything less. And it feeds you into a distribution function that we call CDF. It looks like this. And the probability by the time you get to here of your max value, say this max value is 10, then we know that we have to have had one of these values occur, right? So our probability that we're less than 10 is 1. This is probability that we are less than. Okay, next, we're going to look at types of distributions. So this chapter is going to focus on the uniform and the exponential distribution. To be perfectly honest, these are not widely used. We're going to talk about them because they're useful as thought processes, but the workhorse is going to be the normal distribution, which will be the next chapter. So for continuous probability functions, for a uniform distribution, we're going to have something that looks like this. And we know, this will be in the next slide, but we know this is going to be equal to 1 over, we're going to just call this 9 instead of 8 point something. But the height is going to be 1 over 9 minus 2, which is equal to 1 over 7. So we can easily find this shape of the area. This is just geometry here, right? So we're just going to do 1, 2, 3 times 1 over 7, and 3/7 is the area under here. Now, what are we really talking about when I say that? Well, think about the way that I did that, right? I assign an equal probability to each of these. It could equally be 6, it could equally be 3, and it's uniform, right? Hence the name. So there is no bell shape. This is where you would see the bell shape. Instead, there is an absolute equal chance that we have any of these values. different ways now, so I'll stop there. But it's represented by a line, which, as I said, that line is going to be 1/7. And that function f of x is going to equal the line, which is equal to 1/7. And we're going to take area under that, which is going to be this region. Apologies. Alright, and as I said before, we're going to pay a little bit of attention here to notation. This is the U stands for uniform distribution in between A and B, where A is our low bound and B is our high bound. So going back, we have A is our 2 and B is our 9. As I said, f of x, which is that value on the left, is determined by 1 over b minus a, the high minus the low. They all have equal probability, which is why that is possible. And lastly, we have the theoretical mean and the standard deviation, which is just a plus b over 2. What do we expect? We expect the middle of those values. Doesn't change as much as you would think, but yeah. And the standard deviation is listed there as well. Like I said, it's pretty straightforward. The key is going to be understanding where you're less than, where you're greater than, so which area you're trying to find, and then also finding this little height over on the left, which is going to be what you multiply your odds by. Or this is going to be your odds, what you multiply your outcomes by. And a key piece to continuous probability functions, we're talking here about ranges, right, between these two values. Notice it's not a big deal if I put really greater than or equal to versus greater if we include that bound. I mean, it is technically incorrect, but it will barely change your answer, because what is the probability of having exactly 8? Okay, exactly 8. It is really, really rare, right? Because you've got 8.000001, 7.0 or 0.9999999, and there's an infinite number. So actually, each individual value has a infinitely small chance. So you really have to look at areas and regions to give it a more holistic or a more calculable outcome. Putting this in words, in English, I guess. Think about height. What's the odds that somebody is exactly 7 foot tall, right? 7 feet, 0 inches, 0, I don't know if they exist, nano inches, absolutely no other decimal. Instead, we say 7 foot, and we usually mean about 7 foot, right? So we might be saying 7 foot and can count 6'11" to 7'1" as people who are 7 feet tall. That's kind of the key. You have to work in ranges. We'll stop here.